This is Group A01's video for the Mechanical Design Sprint 2. The first stage of the sprint was to develop a bidding strategy, and we decided to go for spending 400 sprint coins on every single box, apart from boxes 31, 33, and 34. This is because each of those three boxes contained only a single item, and we felt that that would have made the challenge exponentially more difficult. We ended up with 5 boxes.
Design A, the slingshot ball, had the highest scores in the two largest contributing factors, the ease of release and displacement potential. Design D, the car, also scored highly in these categories. However, the potential for the car to tip when hitting a bump in the road caused the score and displacement to be capped at a 4. The Pew matrix allows for a comprehensive assessment on which design maximises the most important considerations. Other designs, such as the plane, scored highly on the weight section, as they were extremely light, which suggests that the Pew matrix alone is not a foolproof method of deciding the best design. This is why the weighting of each category was taken into account to balance out the high scores in less essential areas.
We derived an equation linking the horizontal displacement of the sphere from the end of the board when it reaches the ground, and the angle of elevation of the board from the ground. We derived this equation using existing dynamics knowledge of inclined planes, friction, work energy principle, SUVAT, and projectile motion. In order to derive this equation, we assumed that air resistance is negligible and that the ground is perfectly horizontal.
Second moment of area was used to calculate flexural rigidity, which helped us establish the best orientation of the beam when pulling it back. Bending the bone to its widest side was the best option, as the second moment of area was the lowest, meaning that there is less resistance to bending, so the deflection would be much greater, therefore storing more elastic potential energy compared to bending in the other direction. The spring constant of the bow was found experimentally so that energy conservation could be used to work out the initial velocity of the ball, which was 10.6 meters per second. The energy efficiency was assumed to be 0.5, mostly due to frictional forces between the rope and the metal rods.
Our first designs were all simple sketches of the 4 types of transport we had decided to consider. These were a car, a boat, a plane and a slingshot ball. Each design had to effectively transport the Lego minifigure whilst also making use of the materials given. The final design incorporated the slingshot ball, converted to a crossbow for ease of manufacture, which used the metal frame and rubber plastic arms provided within the boxes. The metal frame had to be sawed with a hacksaw to correctly install the bolts into the arms in order to make the 2 components part of one unified system. The ball was 3D printed with grooves in order to slot the 2 halves together. The holder was also 3D printed on the Ultimaker 3 Extended.
Once we had decided on our final design and knew which materials were available, the final CAD design was created as shown here. This is an ideal version, however due to limitations and errors when making it, a few changes were made which aren't in the CAD, such as string on the pegs at the front, which is used to keep the rope at a set height, and larger holes for the pullback string to pass through to avoid friction slowing down the release mechanism. We wanted to maximise the distance the string could be pulled back, so the crossbow bolts and the pegs at the front are mounted as far away from each other as possible, with a piece of aluminium in between to give a smooth transition for the ball as it's released.
The group predicted a horizontal displacement of 75 meters. However, final testing yielded a maximum distance of 47 meters with a consistency of 4.5 and accuracy to the prediction of 57.6%. On the first attempt, the ball veered off course down a side road, and on the last test, the string succumbed to the tension, preventing a full drawback. Other explanations for underperformance include frictional factors and negligence of the air resistance during calculations. In order to improve the project, solutions to reduce friction around the shaft and release mechanism should be implemented, and to avoid complications in the rolling of the ball, a more consistent incline should have been chosen, for example outside the Lord Bhattacharya building.